I will go live on YouTube now, just a second. Okay, let's start. Hello everyone, and welcome to another talk in our webinar series. Today we have Davide Perna from the INAF, Rome Astronomical Observatory, and he will talk about near-Earth asteroids, risks and opportunities. So before we start, a quick reminder. This webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, LIneA MCTI. So, Davide, thank you very much for being with us today, and the floor is yours.
Okay, thank you very much, Rodrigo, for the introduction. Thank you very much to all for attending. Okay, so I'm sharing, sorry, I'm doing some, okay, I'm sharing my screen. Okay. Okay, can you see it well?
Yes, we can see. Perfect.
Okay, so I will start with just a few words, maybe as maybe not all of you work on solar system science, so just to remind why it is important to study the small bodies of a solar system, because these are the remnants, let's say, of a population of planetesimals that that formed all of the planets and satellites of our system through say a series of accretion processes. So basically, once the planets were formed, most of the material of the solar system was flew away by the solar wind, also by the gravitational interaction. So basically, the population of small bodies that we can see, we can observe today in our solar system represent a kind of time machine that allows us to study the condition that were existing in the early solar system. So almost 4.5 billions of years ago. And of course, as we can study in detail our solar system, also with space missions, we say that solar system science is also important because can be considered kind of a case model to study also all of the exoplanetary systems that we are discovering more and more. And in particular, today I will speak sometimes about primitive small bodies. When I say primitive or evolved, I mean thermally evolved in the sense that when the solar system was forming, as you know, in the closest regions to the sun, the temperature was very high, so hydrogen could not condense. And again, the solar wind, sorry, there is some kind of, the solar wind was, let's say, putting this material away. So the planetesimals that formed within the so-called frost line were composed just by rocks and metals, while beyond this frost line, so in the outer part of the solar system, also hydrogen carbon compounds could be integrated, let's say, within these planetesimals. And today it's say possible to discriminate between these two kind of small bodies just by looking at their spectra. So here I put just some template example spectra of asteroids belonging to the S complex, where S stands for silicaceous, so rocky objects that are formed close to the sun, and C complex asteroids, so carbonaceous asteroids that formed farther away from the sun. And these carbonaceous objects are important also because basically they represent the most probable source of Earth's water, of Earth volatiles, also of organic molecules, because of course the Earth was formed inside the frost line, but we know that these primitive asteroids probably could bring all of this, let's say, prebiotic material, so water and organics, thanks to the planetary migration that took place in the first hundreds of thousands of years after the solar system formation. So here you have basically in red the volatile depleted thermally evolved planetesimals, and in blue the primitive ones. So those with rich in organics, rich in water and volatiles. So here you have the time evolving, and you can see that when the planets, so you have Jupiter to Neptune with the black dots. So when they move, basically most of these planetesimals are scattered away, and you can see that all of the primitive material that can reach the Earth, basically it's enough to bring several times the water that today we have in our oceans. So for sure, these asteroids could contribute. And also, if you look at the isotopic ratios, you can see here you have the nitrogen and the hydrogen, so deuterium over hydrogen. And you can see that the terrestrial values are very close to those measured in carbonaceous chondrite meteorites, that are these meteorites that come from the primitive asteroids. So while, for example, comets usually present larger values of isotopic ratios. So most probably these primitive asteroids are the, let's say, main source of the terrestrial water and terrestrial organics. And up to now, we didn't have, let's say, direct information, but we will have soon, because as you know, there was the Hayabusa 2 mission that just last year took back to the Earth some samples of asteroid Ryugu. And here I put just some results that we got from the orbiter. And so here you have a spectrum, and you can see that around 2.7 microns, there is this band which is associated with magnesium-rich phyllosilicates, so silicates where that were hydrated, let's say. And on the right here, you have a distribution of these phyllosilicates, actually of a band over the surface of Ryugu. So it's normalized to 1. So, but you can see that values are very close. So in blue, it's 0.9 up to 1.10. So basically, these hydrated silicates are basically ubiquitous over the surface of Ryugu. So this will be the first time that we can study in detail such primitive material in our terrestrial laboratories. For sure, that's not enough, in the sense that we have so many small bodies, so many asteroids in our solar system, that it is important, let's say, to couple the space missions with also surveys from the ground to study, let's say, the population in detail. Also for example, investigate how much primitive material is present in the solar system, and in particular within the nearer asteroid population. So to better, let's say, quantify how much of this kind of material could reach the Earth in the early phases of a solar system formation. And ground-based, let's say, observations are proven to be very, let's say, important, because, for example, here I put some spectra that we got with a very large telescope at ISO in Chile in 2017. And basically, from this ground-based spectra, we suggested that the surface of Ryugu was quite homogeneous. So the differences in the actually, we also got more than 3 spectra, and at different rotational phases, all of the spectra were very similar. So we guessed that the surface was quite homogeneous. And also we found that the only meteorites that could fit these spectra, which are nice because let's say they are from 0.35 up to 2.1 microns just in a single shot. So the only meteorites well fitting were thermally evolved carbonaceous chondrites, so CM and CI. And basically the same results have been found by the NIRS-3, the spectrometer on board Hayabusa 2, because also in this case we found a quite homogeneous composition, and again that CI and CM chondrites, especially those that have been thermally evolved, are the only one that could fit well the spectral data of this asteroid. And so today I will speak more about the near-Earth asteroid population, as Ryugu is. And this is a nice plot. It's not very recent, but I like it because basically here you have the Earth at the center. So the blue line is the orbit of the Earth. And all of these dots, colored dots, are asteroids approaching the Earth in this 2007, 2008 timeframe. So the square is kind of, if I remember well, 20 million kilometers. So it's not so close, but you can see that basically we continuously have asteroids that pass very close to our planet. And at this time, the population of asteroids that was discovered was less than 5 times the population that we know nowadays. So you can see that in the last year, there is really an exponential growth of the number of objects discovered. And still, this is a teeny fraction of the population that exists. So basically, really, it's very common to have close approaching near-Earth asteroids to our planet. And here is just another animation that shows, let's say, with these green dots, how many of these bodies are orbiting close by. And in general, near-Earth asteroids are very important to study because, of course, being very close, they can allow us to study very small size bodies. And in the next slide, we will see why this is important. As I said early, as I said before, these objects the objects are important also to constrain, let's say, the delivery of such prebiotic material to the early Earth. And as they are quite close, they are also accessible targets for space mission, for science, of course, but also in the near future, probably to use their resources in terms of water, of mineral, etc. And as we will see also in the following of this presentation, they also represent a risk for our planet, for life on Earth. So we also have to study them to be ready, let's say, for planetary defense issues. And let's say that here you have a plot with the number of asteroids as a function of their absolute magnitude, h, which roughly correspond to, let's say, size in diameter. And of course, also the number of asteroids on the left here corresponds on the right to the impact intervals in years, while the diameter, the size, corresponds to certain impact energy in case of a collision with the Earth. So in blue, you have, let's say, the expected population. In red, you have the discovered population. This is, say, this plot was made in 2014, so for sure now we have discovered more. But in general, let's say that we discovered basically all of asteroids of a kilometer size, while if you go to smaller and smaller asteroids, let's say we know very, very few of them. So basically we discovered just maybe 1% of 100-meter large asteroids. And these bodies, let's say, the smallest they are, the more difficult they are to not only to discover, but especially to study, because these small objects, so just a few tenths or few hundreds of meters in size, are usually quite faint, and they become bright enough to be studied only when they have very close approaches with the Earth. So usually they are the discovery apparition, so when they are discovered, can be, let's say, the brightest time to observe them for years or even decades. So it is very important to study these objects soon after their discovery. And this is important because these small asteroids are also the, for sure, the most frequent impactors on the Earth. And also there are a number of papers happening now that show that when you go below around 200 meters inside, you have quite different composition, different physical properties in general. So different compositions, different rotations, etc. So this also gives us the opportunity to study different regimes in terms of different physical properties of the asteroid population. And so this is why a few years ago we had a survey with an NTT telescope at LINEA, which was the first one fully, let's say, dedicated to small near-Earth asteroids, and we started to find nice results because, okay, these were the literature at the time, which was mostly for larger asteroids, and these are the data that we got at NTT. And so, for example, here you have the, let's say, the distribution of the different taxonomic classes. For example, you can see that we found much more D-type asteroids within this small asteroid population than in larger ones. And D-types are, let's say, the most primitive asteroids, so asteroids that form quite far from the sun. So here we have the distribution today of the different astronomical, the taxonomical types with respect to the heliocentric distance. And so if this result is confirmed, it means that the contribution that asteroids add in bringing this prebiotic material to the Earth could be even more important than previously foreseen, because we see that if you go to smaller and smaller sites, so which are also the most frequent impactors, the percentage of primitive asteroids increases. So we got more data, especially with the TNG telescope, the Italian national telescope in Canary Islands. And also, so we combine basically the previous NTT data with new TNG data, with also literature data. So for more than 1,000 asteroids. And again, here you have a distribution of the taxonomic types as a function, in this case, of the absolute magnitude. So I remember that the higher the magnitude, the smaller the asteroids. And so you can see again that if you look at the D types, indeed, it seems that if you go to smaller asteroids, so higher magnitude, you have more objects, primitive objects, and also, for example, for the K and L taxonomic types that also present primitive material, it seems that they increase in percentage if you go to smaller sizes. So this is a very, very nice result, especially considering that this goes, let's say, against the observational bias, because of course these primitive objects are darker than the other ones. So in principle, they are more difficult to discover. So if you go to smaller and smaller bodies, you should expect to have less of these ones. So if you find more primitive asteroids, despite of a observational bias, this probably means that indeed there are much more of them. But still, the statistics are quite limited because, for most of the classes, we are speaking about just of a few tens of objects. So we should increase this database. And this is one of the main goals of this project, NEO-ROCS, which stands for Near-Earth Object Rapid Observation, Characterization, and Key Simulations, which is a project financed by the European Commission, which is led by our group here in Rome Observatory. And so again, in this project, one of the main goals is to have a very rapid response characterization, both from the dynamical and physical point of view of near-Earth asteroids that have been just discovered. So here you have the list of the partners. The project started last year in January. Okay, we had some problems because during the pandemic, most of the telescopes were closed, so we are a bit late with respect to the programs, but we are confident that we can, at the end of a project, we can fully reach our goals. So I won't speak too much about NEO-ROCS, but I want to speak a bit more about the risk that this object represents. So for sure, there are different, let's say, cases. So in the worst case, let's say you can have a huge asteroid 10 kilometers in size, like the one who hit the Earth about 65 million of years ago. So causing, let's say, a huge mass extinction, including dinosaurs. But, and of course, here you have, let's say, an impact on average every tens or hundreds of millions of years. So this is something that luckily doesn't happen often. But if you go to smaller and smaller bodies, of course, the frequency becomes more important, and still the damage can be quite large. So, for example, if you have objects of tens of meters in size, which can fall about every thousands of years or tens of thousands of years, these objects can still, let's say, release an energy equivalent to thousands of Hiroshima bombs. So basically, if this impact in the Arizona desert was happening today in a large city, you could have millions of people dying. So it's important to take care of these small objects. And of course, if you go to smaller sizes, here you have the Chelyabinsk event in 2013. So maybe you could have some news from this event. And it was a very teeny asteroid, so just about 15 meters in size, which exploded at, I don't remember how many kilometers, kind of 10 kilometers, 20 kilometers, I don't remember, in the atmosphere. So in this case, was just the shock wave, let's say, reaching the surface that caused a lot of damages. So there were tens of millions of euros in damages. There were thousands of people that were that had wounds, especially from exploding windows. So, and this was basically just a very tiny object. So here you have a picture of a largest meteorite that was recovered from this lake when the ice is melted. And so even very small bodies could provoke, let's say, important damages if they hit a city. Okay, here I just put for reference the only case of a person that was hit by a meteorite. In this case, was this woman in Alabama in 1944, 54. Sorry. So she was watching TV, and the meteorite just broken the roof of her apartment and hit her on the side. So here you have the objects, and so just to say that, of course, different scales, but each of them has to be taken into account. And for example, this is the so-called Torino scale, which is a simple way, let's say, to classify the asteroids in terms of their impact risk. So basically, this is done in terms of kinetic energy that they could release on impact, which corresponds, of course, to the size on average, and in terms of a probability of impact. So basically, zero scale means that the object is has a very low probability of impact, or that even if it is certain that it will hit the Earth, the size is so small that it doesn't represent a risk. And then you have higher and higher values up to the red zone here, 8, 9, 10, where basically you have an impact which is certain, but the differences are just, let's say, in terms of the extension of the damage. So more or less, if you have an object smaller than 100 meters, you will have just local consequences. If you have an object, let's say, of a few of some hundreds of meters, you can have more extended regions affected, and usually 1 kilometer is considered as the threshold to have a global effect. So if you have a kilometer-sized asteroids hitting the Earth, so basically you have a global effect around the globe, for example, because you have a lot of material that is ejected by the impact, and so you cover, let's say, the sun, so the winds, let's say, move, transport all of the dust all over the planet, and so basically you could have a drop in the temperature, etc. And of course, this let's say 10 scale cases are very rare, but this is not a reason to don't worry, in the sense that we should not panic. But here we have a dinosaur professor explaining that an asteroid of such size can impact the Earth just once every 10 million years, 100 million years. And so the students ask, so why should we worry? Because statistics is like this. So once every 100 million years could also mean tomorrow. So we should be ready to every possibility. And so this is why there is a lot of work on different types of space missions that could be used to deflect an asteroid which is in route of collision with the Earth. So here I put the three most studied, let's say, technique, let's say the most realistic. So basically, if you have a very small asteroid, you can use a gravity tractor, which is a tractor. So basically, you just put a spacecraft, let's say, hovering at a certain distance from the surface, and so the gravitational traction of a spacecraft, even if very small, works on a small asteroids, especially if you have a lot of time, and you can move little by little the orbit of asteroids. The opposite case, so if an asteroid is very large, you can use nuclear deflection. Even in this case, I want to stress that usually you don't want to disrupt the asteroid. You don't want to destruction, because you cannot know which will be the outcome of such destruction. So what is more safe, let's say, more wise, would be to have a nuclear explosion at some distance from the asteroid, and basically, again, let's say the radiation that hit the surface will provoke the evaporation of some layers of the surface. So this will give a momentum in the opposite direction to the body. For cases in between, let's say, you can use a kinetic impactor. So basically, by definition, is a spacecraft which is launched at very high velocity, so around 10 kilometers per second against a colliding object, and again, you can move it from its dangerous orbit. And here I put just a very rough, let's say, image where you have the different fields, let's say, of application of the different techniques. So basically, if here you have the diameter of the asteroid and the warning time that you have before the impact. So if the object is very small, just a few tenths of meters in size, you don't want to do a space mission. So it's easier to just have say evacuation of the impact region. If the object is larger, so then 50, 100 meters, you can use one of these three techniques. As I said before, you can use the gravity tractor only if the object is quite small and you have several tens of years of time to move it little by little. In the intermediate case, you can use the kinetic impactor, while if the object is very large, let's say kilometer size, or if you have not so much time to launch a kinetic impactor, you can use only, let's say, a nuclear device. And of course, this is important to stress that in this case, you need a spacecraft which is ready to be launched once you discover such a dangerous body. So if we discover, let's say, an asteroid that needs a space mission within 2 years, so usually when you build a space mission, you need more than that. So you can spend 5, 10, 15 years. So there is a lot of discussion in the international community to have kind of ready to launch spacecraft, especially kinetic impactors, in case we discover such a danger for our planet. And it's important to stress that these techniques in principle works very well, but none of them has been tested until now. But it will be soon. So here you have a schematic view of the DART mission by NASA, so the Double Asteroid Redirection Test. So maybe you know this mission that will be launched later this year in November, and in September 2022 will impact the secondary member of a binary asteroids, Didymos. So Dimorphos is the name of a secondary object. And so DART will impact this body and will change the orbit of a secondary around Didymos. So let's say this is not yet a full-scale experiment, because of course it's much harder, much more expensive to change the heliocentric orbit of an asteroid than to change, let's say, the relative orbit of a binary asteroid. So, but still, it's the first, let's say, planetary scale experiment. And in this case, DART will have also a small CubeSat traveling with it. So LICIA, which is an Italian spacecraft, was scientific team is also led by Elisabetta Dotto in our group in Rome Observatory. And so basically, LICIA will be detached around 10 days before of the impact, and will observe the impact of DART. And so in particular, the main goal will be to observe the ejecta that will be created by the impact, the crater that will be formed, and also to look at the opposite sides of a asteroid, because of course DART will impact on one side of Dimorphos, while LICHA cube after the impact will fly by Dimorphos, and so will also be able to image the opposite side, so to reconstruct the three-dimensional form of Dimorphos. And the change that is expected to be reached with this experiment is around 10 minutes, which is easily, let's say, can be measured quite easily with observations from the ground. So there are a lot of campaigns already that the DART team, the LICHA cube team started in the last years to measure in a very high precision, which is the orbital period of Dimorphos. So it will be easy to measure the change that will be provoked by this impact. And here I just put a small video that will show what I just said. So here you have the LICHA cube CubeSat that is detached from the main spacecraft and days before the impact. So it will be an automatic routine to impact the asteroid. So LICHA cube will image the plume that will be created. We will also have the crater, and also, as I said, the far side of the asteroid. And in the last part of this talk, I also want to stress that for sure near asteroids represent a risk, but they also are a very nice opportunity for us, because as they are very close to our planet, so we can study many of them with space missions. So you can compute orbits that allow to visit more than one asteroid with a single spacecraft. And as I said before, as they are very close, this gives us the opportunity to discover very small asteroids, so down to the meter scale. So we have objects 2 to 3 order of magnitude smaller than what we can study in the asteroid main belt. And so these small asteroids are completely not only unexplored from spacecraft, but also we basically know very, very little about them. And they are very important because they can give us inputs about which is the aggregation of these small bodies. So for sure we have dust particles, we have meteorites. We can see large asteroids today, but we don't know how these asteroids were formed. And so here is a very, very, say, simple plot. It's not very updated. It's a paper in 2011. But you know that basically it's easy from dust particles to make, let's say, centimeter size grains just by non-gravitation forces, so but viscosity works. And once you can form kilometer size objects, so planetesimals, again, gravity works very well. So you have a runaway growth to form larger and larger asteroids, to form planetary embryos, and then planets. The problem is in between, so in the so-called meter size barrier. So because here, so nor gravity nor viscosity can work, because the relative velocity starts to be very, very high. And so basically the impacts destroy particles instead of forming larger ones. So it will be important to study meter-sized asteroids or tens of meter-sized objects to see how cohesion works in such a low gravity regime. And so this was, let's say, the rationale behind a proposal that we sent to ESA, the European Space Agency, in 2018 for a fast mission call. So this was called the Near Space Tracker, which was selected together with other 5 proposals for a phase 2 proposal. And very schematically, so basically the goal was to rendezvous with multiple near-Earth asteroids, so at least 2 in the baseline mission. So the first target was 2012 LA, which is just a 20-meter asteroid, and then the second target was Asteroid Apophis, which is very famous or infamous, you know. So 2029 will have a very high, very close approach with the Earth. And so in our proposal, basically we had a mother craft and a daughter craft to be released around Apophis, and we had a radar static radar investigation to have a radar tomography of interior of Apophis. Unfortunately, our proposal was not accepted because of two reasons. So the radar technology was considered not enough ready, mature for the launch, because basically in this proposal, this call, so basically was to launch a small spacecraft with Ariel in 2028. So for sure, ESA was not accepting to take risk, let's say, in this sense. And also we had a quite low delta V, so you know the velocity change that you need to reach Apophis. So we had not so at so large margin. But let's say that the scientific assessment was very positive. So we had the idea to apply again for next mission opportunities. And this happened last year because ASI, the Italian Space Agency, had a call for future CubeSat mission, also in the framework of a program by ESA. And so we presented this plan to launch a space mission with a CubeSat with 2-year operations after a 15-month development plan. And the idea was to study asteroids that are both very interesting in terms of science and in terms of impact risk. So the goal was to rendezvous with a decameter size, with a very small near-Earth asteroids, which also presents high impact risk. And during the cruise, also to fly by 2 potentially hazardous asteroids, which also present interesting physical properties. So the idea is to use commercial components, COTS, so to have a very low cost, low risk, but still high return in terms of science mission. And here are the baseline scenario. So with a launch in late 2026, we should have 2 flyby of these 2 potentially hazardous asteroids in mid and late 2027, and then rendezvous in 2028 with our final goal, which is 2000 SG344, which is a 40-meter asteroid. So it's an order of magnitude smaller than Itokawa, so which is the smallest asteroid visited today. And also this asteroid is among the most risky and the most accessible targets also for human exploration within both ESA and NASA risk list. And as I said before, also the PHAs have nice appealing physical properties, because both of them could have quite high albedo values. So the surfaces could present some material that are still unexplored. And also the second flyby target also has a diameter below 200 meters. And this is important because most of you know that 200 meters is more or less the threshold between rubble pile asteroids and asteroids that have some cohesion. So here you have a frequency of a rotation as a function of a size, of a diameter. And so basically you see that all of the asteroids larger than 200 meters present this spin barrier. So basically this is a barrier which is given just by the gravity, say the breakup of a body given by the centrifugal forces for objects that are held together just by gravity, so the so-called rubble pile. Why, if you go to smaller bodies, you can find objects that spin much faster. So it is very important to study one of these bodies that by now we never explore. So basically, both the main target and the second flyby target will be in this region. And I'm almost finished. Just to say that in the baseline scenario, as I said, we have a launch in late 2027. Here we have the relative orbits of a spacecraft with respect to the Earth and the 3 asteroids. The delta V is quite low. We have a lot of margin. And so this gives us also quite large flexibility because we can change easily the launch dates and also the targets. And here is the preliminary design of a spacecraft, which is a 12-unit CubeSat. As I said, all of the components are commercial. Most of them already flew in the low Earth environment. And also the payload is composed by 2 cameras, which are commercial. So we renamed them NemoCam and Pharos for this mission. And with these cameras, basically, you have a field of view, spatial resolution, and the minimum distance to focus. So basically, for both the flybys, we will have quite fast flybys, around 10 kilometers per second. That's 50 kilometers of distance. So basically, the images will have a resolution about of 10 centimeters. So will be enough to study the crater size frequency distribution, the boulder size frequency distribution. While for the rendezvous with the final target, we will have also a 2-month, at least 2-month campaign around the body. So where we'll have several close passages close to the surfaces. So in this case, we can obtain images down to the centimeter scale, and also this will be important to have a radio science experiment, so to study, let's say, the gravitational field of the asteroids, and these 2 data set will also represent the input for, let's say, 2 kind of numerical simulation that our group will perform, both for streaming stability and body simulations, to understand how this small bodies can form. And of course, this will be also useful to refine the orbital eccentric orbit of these objects, and also the non-gravitational effect, Yarkovsky, etc. So to refine also the impact solution that this body present in the next tens of years. And so I finish just to say that this ANIME proposal has been selected. So after a technical and scientific screening. And right now we have a financial evaluation, which is ongoing with the Italian Space Agency. So we will see, so fingers crossed to be ready to fly soon. And this will be a nice way, let's say, to have a very low cost but high scientific return missions, which also has a technological importance to test in the deep space some new solutions. And I hope I'm not too late, and I thank you very much. I hope that Google Translate work with Brazilian, and so muito obrigado. Thank you.
Okay, thank you, Davide, for your remarkably interesting talk. Your Google Translator worked perfectly fine. Okay, now we have some time for questions. If you joined us on YouTube, you can post your question in the comment section and I will redirect it to our speaker. If you joined us on Zoom, you can raise your hand and ask your questions. So we have the first question, Nicolasi, go ahead.
Hi, well, thank you very much for coming. Great talk. First of all, I'm panicking already. I mean, that video that you showed is really mind-boggling. I mean, they miss us because they don't know where they're going. I mean, it's the second question is, I mean, it's the second time I hear about exploration of asteroids. But how is that envisioned? Because to break even, you would have to have a container that would go there to the asteroid to get whatever minerals we want and to bring it back, right? I mean, but this would be very expensive to take off from Earth. So how do people, and also you have just a window of opportunity, right? I mean, you have to go there to the asteroid, do whatever the mining that you want to do, and then come back before it takes off further away from Earth. So how is that envisioned? I mean, is it realistic?
Let's say for mining, you mean?
Yes.
Okay. Let's say that I attended a workshop about that a couple of years ago, and I think we are not yet there. So right now it is not, let's say, from an economic point of view, is not yet convenient, let's say. But there are a few companies, private companies, they are starting to study this kind of let's say, possibilities. And the main idea is not to bring back to the Earth this material, but to use this material in space. So for example, to use asteroids kind of stations when your spacecraft can stop and bring, so for example, from water you can derive hydrogen and use hydrogen as a propellant. Also to use, for example, the regolith, so you can build something in space. So you can go to an asteroid with kind of a 3D printer and use the material of the asteroid to build something that would be much more expensive to be built on Earth and then launched in space. So it's still kind of science fiction.
So, I mean, they're imagining some station in the moon or Mars and just using that okay, that makes sense.
I think so. Then for sure there is also there are a lot of rare metals on asteroids that are much more abundant than on the Earth. So I guess that at some point, once let's say this kind of traveling in solar system will be easier, at some point will be also convenient to go there, let's say, mine these metals and bring them back on the Earth.
So we are not talking, certainly not talking about that in my lifetime, but anybody.
I don't know. Why not? Why not?
Okay. Thank you.
You're welcome.
Thank you. More questions? Okay, Kavana, please go ahead.
Hi, David.
Hi, Helga.
How are you? Long time.
Yeah.
So I find your project very interesting, the one you're trying to fund with this Italian Space Agency. But do you have any capability to try to narrow the composition of the objects with the instruments you plan to have aboard the probe?
You talk about the anime. Yeah. These objects you're speaking about.
Yes,
Okay.
yes. I guess you're using off-the-shelf cameras and RGB cameras.
Yeah,
So,
okay.
is there any way to?
So let's say that when we selected the asteroids to be visited, we checked that they had observability windows in the next years. So right now we don't have any information about the composition of these three bodies, but all of them could be observed. So the idea is that if a mission is approved, we will have the possibility to ask for observational time to constrain the composition, the rotational period, etc. So this was one of the, let's say, requirements in the target selection, that it will be possible before the encounter of with the space mission to study them from the Earth.
I see, but the probe itself, it won't not have any capability to say much about the composition, to put constraints on the composition, because you only have RGB cameras, right? You don't have
Okay.
you don't have filters.
Sorry, yeah, no, I didn't understand well your question. No, yes, you're right, because we have just a RGB camera. So from the space, we won't be able to study in much detail the composition. Let's say that for anime, because of course, if for this proposal, the cost of emission was a very important parameter. So we could not have a spectrometer, let's say. And so we prefer to have just a camera, two cameras actually. But let's say that in this case, the goal would be to get a good idea of a composition already with ground-based observation.
I see.
At least the main taxonomic type. And the main goal of anime is not too much to study the composition, but let's say the cohesion status. So to see, so the shape of the object would be more important. For sure, the composition is also important, because different composition could be, let's say, could also, a different composition could also influence the way how this material formed to build the asteroid. But the main goal, let's say, is to study how this object is held together. So the main idea is to get images and to have these close flybys, to have a radio science experiment, to study as much as possible, which is the internal mass distribution. And so you can use the radio science as a main driver for the data, and also from the images, try to get some constraints from the fractures, from the boulders that you can study, and try to understand which is the internal structure of a body. Then we will see, in the sense that this was just a first proposal. If we will have a possibility to have more, let's say, more powerful instruments on board, this will be for sure an opportunity to be taken.
All right, it's a very nice proposal.
Thank you very much.
Thank you. There is also a question in the chat from Autumn Winter. He asks, what is the order of the cost of the anime mission?
Okay, hello Autumn, first of all. And the order is, let's say, a few tens of millions of euros.
Okay. Well, I also have a question. We were speaking about space-based missions, but you told us about the New Rocks project that is more ground-based. So how does it work? And also another question is, given that you even pointed out the LSST in the beginning, How will you benefit from it, and what are your strategies for those new discoveries?
Yeah,
To follow up.
Yeah, no, thank you for the question. Let's say that new rocks, it's a consortium, let's say, as here you can see the list of different partners. And basically you have both research institutes and industries. So the idea is to have kind of synergy of European partners, and industries are more working on the, let's say, dynamical part, while we, let's say, scientists, we are more working on the physical characterization. And the point, LSST for sure will be very important, because this will have a huge number of objects characterized, but it will be only, let's say, photometry. So the idea is that here you want to study in very much detail very small object just after the discovery. So because basically when these tens of meters of asteroids, at the moment of a discovery, they have a magnitude around 20, 21. But then after a few weeks or after a few months, they can become very faint. So they have magnitudes of 27, 28, 30, or even fainter. So the idea is that as soon as these objects are discovered, we have within NEROX also some colleagues working on a priority list, which we use to identify the targets for our observations. So where, for example, the observability windows in the next years, of tens of years, is one of the main parameters. So the idea is to have a very detailed characterization where we get spectra, we get light curve. So we try to have a very complete characterization of these objects. And for sure, with service like the Vera Rabin Observatory, you can have a statistical coverage, let's say, while here we more want to focus on specific targets and have a very deep characterization. So let's say in this sense they are complementary.
Yeah, that's amazing. I think you will have already some information on light curve from LSST, since it will sweep the sky every 4 days, every 4 nights. So during the discovery, you might be able to measure something like rotation. Okay, thank you. I don't know, Carvana, do you have another question, or is just your hand still raised?
No, my hand is still up. Sorry.
Okay. So we have more questions. Okay, well, if there are no more questions, we will now wrap this up. Let me just say a final words. This presentation will be available on our website and on LIneA's YouTube channel, so you can revisit and rewatch it if you want. And for the next week's webinar, we will have Carlos Bengali here from the Observatório Nacional, and he will be talking about observational tests of the fundamental hypothesis of cosmology. So thank you everyone for attending, and a special thanks to Davide. Thank you, Davide.
Thank you very much to you for the invitation and for attending.
Okay. Thanks for taking your time, speaking to us today. And everyone, have a great day. Stay safe, and I hope to see you all back next week. So have a great day. Bye-bye. Thanks.
Bye-bye.
Davide, I think you were made host.
Okay, so I